Alright, in this session I'm going to talk a little bit about simple differential equations. We're not going to delve too far into this topic, but I will mention it so you've seen them a little bit. So, in short order, this will be in your textbook as well, an equation involving a derivative is called a differential equation. The order of a differential equation is the highest order of derivative, the highest derivative, I guess, involved in the equation. So a second order differential equation would have a second order derivative in it, or d squared y dx squared, and so on. A little bit of work with solving them. We're not going to get into really complex ones. This is example 1 of page 325, and we're asked to find all functions y that satisfy the differential equation dy dx equals secant squared x plus 2x plus 5. Now, we're not really doing anything new here that we haven't seen before. We're just talking about it a little bit differently. I'm going to solve this differential equation for y. Basically, find a function y that makes this work. Now, if the derivative of y is equal to this, how do I find y itself? I take the antiderivative. So we anti-differentiate to solve. So y is just going to equal the antiderivative of secant squared is tangent. The antiderivative of 2x is x squared. The antiderivative of 5 is 5x, and then we end up with a constant of integration, or constant on the end. And that is my solution to the differential equation given. We might also call this the general solution to the differential equation. Now, it's not always about general solutions. Sometimes we have some more conditions involved that let us get to a specific solution or definite solution. This will be example 2 on page 325. And again, it's not going to be anything really different than things we've seen before. We're just couching it a little bit differently, phrasing it a little bit. So in here we're asked to find the solution to the differential equation dy dx equals e to the x minus 6x squared, whose graph passes through the point 1 and 0. So again, to solve, we anti-differentiate, and we get y equals the derivative, or the antiderivative of e to the x is simply e to the x. The antiderivative of negative 6x squared is going to be negative, and x cubed would have to be involved, which means our number in front would have to be 2. And then I'd have a constant. But I need to satisfy this specific restraint as well. And x equals 1, y equals 0. So 0 equals e to the 1, or just e, minus 2 plus c. Rearranging c equals 2 minus e, and my definite solution is e to the x minus 2x cubed plus 2 minus e. Now, sometimes it's easy to leave things, or easier to leave things a bit more general, which we'll see in the next example. This is example 4 off of page 326. And we're asked to find the solution to f of x equals e to the negative x squared, where f of 7 equals 3. If I wanted to restate this differently, I'd say dy dx equals e to the negative x squared, and at x equals 7, y equals 3. That would be the same setup, the same statement. Now, my problem is here, this is harder to anti-differentiate. We don't really know exactly how to deal with an exponent inside the exponent here yet. But what we can do is leave things a little bit more general. Another way we have to talk about an antiderivative is the integral. So if f prime of x equals e to the negative x squared, then I can certainly say that f of x would have to be the integral of e to the negative x squared dx, as long as my upper limit is x. Oh wait, sorry, I should switch my variable here so that I can put x as the upper limit of my expression. And I'm going to make my lower limit 7 for a reason which is going to come out here in a second. And some constant that we get tacked on to the end. So I know the derivative of the constant is going to be 0. The derivative of this thing is just going to be e to the negative x squared. So this satisfies this differential equation. Now with the specific case, at 7, this is now my integral. And the whole thing has to equal 3. But if I take an integral from 7 to 7, that's just going to go to 0. That's why I chose 7 for the lower limit here, because when I filled in the definite value of x that I was given in my statement, the integral will go to 0 and I'm left with the value for the constant. And so I can generally say that this function is equal to the integral from 7 to x of e to the negative t squared dt plus 3. So without necessarily knowing what that integral works out to, I can still use it in my solution. It's a little bit of a redundant solution. It would be similar to, what value of x makes x plus 8 equal to 12. And I say, well, that value would be 12 minus 8. Works out the same sort of way. The last thing that I'm going to mention, and it's not something that we're going to spend much time on at all really, is the concept of a slope field in a general solution graphically. Slope fields in general solutions. Now, I'm not really going to ask you anything about this. I really just want to show it to you in case it crops up at some point later in time. The concept is not too difficult, but it's a bit picky to sort of work through a lot. And this is kind of stealing off of examples 5 and 6 from pages 326 to 327. And in these, we are given the differential equation dy dx equals cos x. And the first thing I'll show is us constructing what's called a slope field based on this. So if I take a look at a table of values for this, x and dy dx, I know that when x equals 0, dy dx is equal to cosine of 0, which is equal to 1. I know that at x equals pi over 2, cosine of pi over 2 is 0, so my slope is 0. At pi, I know cosine of pi is negative 1. At 3 pi over 2, my slope is 0. And at 2 pi, my slope is 1 again. And that pattern continues over and over again, as you know. What a slope field for this looks like if I increment this pi over 2, pi, 3 pi over 2, get 2 pi in there. Be a little crowded to get 2 pi in there. Negative pi over 2, negative pi, negative 3 pi over 2. I know that wherever my function is situated, at x equals 0, the slope is going to be 1. So to show a slope field, what I show is that everywhere x equals 0, a line with a slope of about 1. At pi over 2, my slope is 0 everywhere. So there, I show lines with a slope of 0. At pi, I know my slope will be negative 1. So there, I show little line segments with slopes of about negative 1. 3 pi over 2, my slope goes back to being a 0. And similarly, if I go back the other way, slopes here is 0. Slopes here of negative 1. Slopes here are 0. This would be a slope field for dy dx equals cos x. Now, I can actually make something that looks like a general solution from this. I'll do that in red. So if I start at a point here, and I sort of follow along up to the next little line segment that I run into, you get that part right? I do. Hooray! A little bit off on that one. And if I do that for any starting point, what I get is a series of curves. Where am I going here? So you see, if I keep doing that, what I end up with is this series of curves that all look a lot like sine x, but they're basically shifted up and down from one another, and what am I showing are all the possible functions that have that as a derivative. So in the red, what we've got is the family of general solutions. For dy dx equals cos x. Now again, that's not really something that I am going to ask you to do anything with. I just wanted to show it because I know that it comes up sometimes later in introductory calculus courses in case you happen to see it later. All you're really doing is making a sort of rough approximation of what the slopes are like at different points. That's your slope field, and then if you happen to connect all those to give functions, what those functions are your general solutions for that differential equation. Okay. I think that was all I'm on to mention with that. So that is it for this session. All right. Thanks, everybody.